Hi, thanks for watching our YouTube video. This is Yan. In this video, we'll talk about a recent paper on a new solution algorithm called BO4IO, where we apply the Bayesian optimization to solve and provide uncertainty communication in inverse optimization. So first, let's start with what is inverse optimization. So in PSC or OR community, we have been using mathematical optimization to model decision-making processes in our life. We will formulate such a forward optimization problems that includes an objective function f and constraint g that is parameterized by some model parameter data. And then the forward optimization problem will take the contextual inputs that describe the system conditions and make the prediction on our optimal decisions at the output. And for data-driven inverse optimization, it describes a special case where we have unknown parameters inside for optimization problems, but instead we can measure the output decisions at different system condition U. Then we can collect these data sets, these observations, then make inference to estimate the unknown parameters. And the following, we're showing a few examples where we can apply such data-driven inverse optimizations. For example, it has been used to understand the customer preferences, learning the expert decision rules in systems, engineering systems, and lastly, how cells making decisions in biological systems. And what makes the inverse optimization special is that it provides explicit constraint formulations, which allow us to have modeling flexibility, incorporating our domain knowledge on systems, and hence the final model become inherent interpretable. In other words, the estimated parameters actually contain some physical meanings, which may make it stand out from the traditional black box approach like machine learning. So how do we typically formulate such problems? So it is typically formulated as the following bilevel optimization problems, where alpha level is similar to the traditional machine learning. We're trying to minimize the loss between observed decisions compared to the predicted values from our low level for optimization problem at different system condition U under this observation data sets. As you can tell from the formulations, it's difficult to solve because the number of the lower level problems actually scale with the number of data points that you have. And typically, the solution algorithm requires single level reformulations based on optimality conditions like KKT or duality theorems. However, this kind of strategy will become challenges when we're trying to estimate the parameters inside um, nonconvex for optimization problems. So this motivates this work. We're trying to come up with an alternative solution method that can apply to general inverse optimization problems. So here's our idea. Instead of applying the single level reformulations, we treat the upper level loss function family as a black box functions. Then we can apply derivative-free optimization method like the Bayesian optimizations to iteratively converge to the unknown parameters and parameter values in our full optimization problems. And this provides us a few key advantages. The first thing, it allows us to avoid single level reformulations. And because of that, we don't have such a limitation on types of for optimization problem we want to estimate. And lastly, although the derivative-free optimization like Bayesian optimization require a function evaluation of the loss functions at each iteration. But since the lower level for optimization problem they're independently of each other, it can be easily parallelized to speed up the computation time. Next, let's work through how does this algorithm work step by step. So first, we initialize our algorithm with randomly sampling the parameter value in your its dimension space. And then we will evaluate the loss function at these different points by solving the lower level for optimization problems in parallels. Then we can collect these different sampling points and use it to construct a probabilistic surrogate of using our big Gaussian process model to approximate loss function value, loss function curve. Then we can use this JP surrogate, which provide uncertain complications on explored regions. Then we can formulate a acquisition function and further optimize it to create the candidate points that can potentially lead us to a better loss function values. And then we can do the function evaluations at the suggested points and use the information to update our GP. Then we repeat the whole process again until we converge to the optimal parameter values. And next, let's use one case study to showcase the efficacies of our proposed algorithms. We were trying to learn the unknown market demands in the standard pooling problems. So in standard pooling problems, they typically try to mix different feedstock with different quality profile in either intermediate pool or final product pool. Like we can generate different kind of products that can meet different quality constraints as well as meet different kind of product demands. So the goal of solving this problem is to identify optimal flow distribution in the pooling network such that we can maximize the overall profit while satisfy these different constraints. And what makes this problem a complex problem to be solved is because the product quality constraint contains bilinear terms, which make it into a nonconvex nonlinear program problem. And in this case, I will assume that the product demands of the market is actually unknown. And then we want to apply our BO4IO algorithm with a set of synthetic data set to estimate the unknown market demands. And here I want to highlight that we only use a subset of decisions to estimate unknown parameters. In other words, our algorithm doesn't require to use all the decision variables inside our optimization problems. And next, we further test out our algorithm on the different kind of benchmark problems, including the Harvard-1 and FOSS3. And the idea here is to test out how does our algorithm work under different pooling network sizes. So here's the result. The left plotting out how testing decision error progress over BO iterations under different pooling networks and at different unknown dimensions D. And here we test out the algorithm on 10 different random instances. In other words, these 10 random instances will contain different unknown parameters values. And we train and test our algorithm with the size of the training and testing data set of 50. And then we generate our synthetic data sets with some white noise level. And if you compare the first two conditions, the Harvard-1 and FOSS3 on the two unknown dimensions, we show that our algorithm is quite robust against different network sizes, where you can see the two conversion curves is actually identical to each other. And next, if you look at the FOSS3 problem with the increasing unknown dimensions, while we do see they require more iterations with a large number of unknown parameters, with our algorithms still very efficient, you can converge to a good models within 50 iterations. And next, we further extend our problem into a generalized pooling problems where it contains integer variables. And we show that our algorithm can still be able to efficiently converge to good models within 100 iterations. Next, we evaluate how much data points that is needed for our BO4IO algorithm to estimate the good models. We look at the FOSS3 problem with the 8 unknown parameters. And we train our model based on different sizes of the training data sets. And we found out that our algorithm is quite efficient. It only requires only 10 data points to estimate the good models. And if you look, and especially when you look at final testing decision errors, you can see no matter how much amount of the data points you put it in, you can always convert to a very low decision error. However, we further look at the parameter loss that compared to the ground truth parameter values. what we found is that while decision loss is low, as we showed in the previous slides, we found out that our algorithm does not always converge to the ground truth parameters, where you can see that we still have quite a bit of a parameter loss when you go up to the final 100 iteration, and especially when we go up to a higher unknown dimensions. And this type of phenomenon where the multiple solutions leads to the similar decision loss is quite a common issue in inverse optimizations problems. And this gives rise to the motivation of the second part of this paper. We're trying to see whether we can quantify the uncertainty on our IO parameter estimates, where there is very few existing work I focus on this regions. So next, let's work through how do we provide the uncertainty quantification in our BO4IO. So let's start with one way to define uncertainty quantification in a parameter estimation problem like inverse optimizations. So one intuitive way to look at the confidence intervals. So you can use a finite sample approach to get the confidence intervals by looking at the optimal loss that you could get from your inverse optimization problems, while also look at the sample loss at the parameter interest of the dimension that you're interested in. And then you define a significance threshold, then you can get the confidence intervals of that. Well, one issue is that how do you get the sample loss? So one common way to do it is use the so-called four-part likelihood functions. So idea is quite simple, where you stay on the dimension that you're interested in the specific parameters, where you fixing it at different parameters values, then you optimize the other parameters to see what's the minimum loss you can get. Then you can construct the profile likelihood curve that's shown on the right-hand side. And then you compare the optimal loss you get from your original problems. And then based on the significance threshold that you define, then you can get this profile likelihood-based confidence intervals. And what makes this powerful for this profile likelihood analysis is that we also provide identifiability of a parameter estimate. And there are three types of parameter identifiability. The first thing is identifiable parameters, where you see that you have both hand side that on your profile likelihood that reach the significance threshold. In other words, it tells us that you have quite high confidence that the ground truth parameters actually lies in this confidence interval. And second type of behavior is where you see this practically non-identifiable parameters, where you see that the one hand side never reached the significance threshold. And what this further tells you is that you might have insufficient data quality or quantity, which you can further improve your models. And last type of behavior is so-called structurally non-identifiable parameters, where you have both hand side never reach the significance threshold. And what this tells you is that these parameters might be redundant to your model, so you can maybe drop that from your model. Or if you really want to identify these parameters, then you might have to include some new measurements to close these confidence regions. However, one thing to keep in mind is that in order to get this profile likelihood curve, it requires you to resolve the problem that these different parameters values along this dimension space, which is what we want to avoid at the beginning for our inverse optimization problems. But what's a good thing for the BO4IO is that after we solve it, we actually get a surrogate, GP surrogate on our approximate profile likelihood, as shown on the right-hand side, where the lower output confidence bound of our GP segregate actually will be able to bounce our profile likelihood function curve. And then if we pick up the lower confidence of our profile likelihood, then we can get the outer approximation of the confidence intervals. That we have a simple proof on paper showed out that you always bounce the original confidence intervals based on the traditional PL analysis, which is the worst case approximation of our confidence intervals. So next, let's apply this PL analysis to our pooling problems, where recall that we have in the issues that our algorithm does not always find the ground truth parameters values. especially when we go to the phosphate problems with the higher unknown dimensions. So then we apply the PO analysis on these different four conditions. And we found out that when we're having a higher loss parameter law errors, this is where we see an increased amount of percentage of non-identifiable parameters inside our problems. And then we further take out the phosphate problem with 8 unknown dimensions and look at one specific parameters. And we found out that when you're training the model with 50 data points, the profile likelihood actually shows out that this parameters is defined as a practically non-identifiable parameters. I recall that they actually tell us that indicates that we might have insufficient data quantity and quality. So then we further increase the data points that we give it to train the models. Then we show that we can actually close the confidence levels and then make it structurally identifiable parameters. In the other hand, we've improved our measurements where we decrease the measurement errors on our noise on our synthetic data sets. We also show that we can convert parameters into a structurally identifiable parameters. And this result aligns to the traditional PO analysis where we can leverage the profile likelihood result to indicate the future experimental designs. And at the same time, I also want to highlight here is that it tells us that we're looking at the inverse optimization problem. When we solve it, we should not only focus on the decision error, but we should also perform this type of uncertainty quantification to ensure the confidence level on our final estimated models. So with that, I want to conclude this talk with a few key takeaways. So in this talk, we first propose a new algorithm based on the idea of treating the upper level loss function as a black box in the inverse optimizations and apply the Bayesian optimization to efficiently solve that. And secondly, in the second part of the paper, we proposed a new profile likelihood analysis where we can get some uncertain quantification of our final IO primed estimates. And then we apply our algorithms in the standard pooling problems and showed out that our algorithm can quite efficiently find the unknown parameters in both nonconvex, nonlinear program or mixed integer nonlinear programs. And lastly, in our PO analysis, we highlight that it is important to look at uncertain quantification in data-driven inverse optimization problems. And with that, I would like to thank your attention and thanks for all the funding sources. And if you're interested in our paper, please feel free to download our paper on Computer Academy. And with that, thanks again for your attention. And if you have any question, please feel free to email us. Thank you.